Hello, today we will talk about AC current and AC voltage measurements. The reason for this video is a little bit mystery measurement on another YouTube channel and the discussion about it. More details after the intro. In the other video, the link you will find in the description, there was following measurement. Via a switch and an amp meter, there was an LED lamp connected to the 220 volt power supply line. While the switch was open, the measurement device showed 21 milliamp. When the switch was closed, the measurement device showed 50 milliamp. On my comments that there's something wrong with the setup when without power already 21 milliamp is measured, I got the answer. This is caused by the technology of the multimeter. And now the big question. When the switch is closed, do we have 50 milliamp or do we have 50 milliamp minus 21 milliamp or do we have something else? Now my view on the situation, what is caused by technology and what not, and finally I will show that the measurement could be done much better. First, the technology caused part of the AC measurements. The generator of the 220 volt power lines is on one side connected to ground and the other side goes via different wires to the different loads. So we get in the room a more or less strong 50 Hz AC voltage field. The measurement wires built with the surrounding tiny capacitors here and here. So we get the following equivalent circuit. A AC voltage source is connected via a tiny capacitor to the internal measurement resistor via a further tiny capacitor to the voltage source. Due to the high resistance of the internal resistor, the current through the tiny capacitor could already cause a significant voltage, which is about some tens of millivolt, in some cases even 100 millivolts, depending how close the measurement wires are to the power supply lines. When we make a shortage of the measurement lines, the display goes down to 1 or 2 at the last digit, which is the basic error of the AC voltage measurement. When we look on the equivalent circuit, it is clear that the small current through the capacitor cannot generate the voltage on the internal resistor because we have here the shortage. If we have selected the AC voltage measurement, then we can see here on the last digit some tens or at some measurement devices even up to 100 or more millivolts. And the reason is because of the very high ohmic impedance here. We have a capacity coupling to the power lines, and depending how far away the power lines, we will see more or less here a voltage. This can be stopped very easily when we short the two lines, and we see that it goes back to the 1 or 2 digits of measurement error in the last digit of the measurement device. Also, twisted measurement wires can reduce the effect of the coupling to the AC power lines. Let us assume the top plate is rising to a positive voltage while the bottom plate is rising to negative voltage. Then this part of the line will become positive and this part of the black line will become negative. And in this area it is in the other way around. This black line gets positive and this red line gets negative. If we have enough windings, then the total effect becomes zero. By the way, the same is valid for the voltage which is induced in this wire loop by the magnetic fields, because we have here a positive loop and here we have a negative loop, and over a lot of loops the total error becomes also zero. Here's a measurement device with open twisted measurement wires. Now we will have a look on the AC current measurement. For this we must know that the current measurement is done in a multimeter by a voltage measurement on a current sense resistor. For current measurement, the internal circuit looks usually like this. We have the input pin, a fuse which protects the multimeter against overcurrent, the current sense resistor, and it goes back to the other connector. Internally there is a voltmeter at the current sense resistor. The current sense resistor has a resistance depending on the current measurement range from some milliohm up to some 100 ohm. This low resistance here protects, similar to the shortage on the voltage measurement, against capacitive coupled signals on the measurement lines. So an ammeter with open lines show only the base error, which is usually 1 or 2 on the last digit. Now we will repeat the measurement from the video. We will see when the switch is open, we see only the base error of the ammeter, and when the switch is closed, we will see the correct AC current. Here's the measurement setup. We come from one power line, go via the red line to the ammeter, via the yellow line to the LED lamp, and from the LED lamp back with the black line to the power line. The ammeter is set to amp, 400 milliamp, and AC. To see the result in the measurement device better, I turn on the lamp, and now we see that the ammeter is still only 1 or 2 digits on the last digit, and I turn on the lamp, and we see 63.9 milliamp. I shade a little bit, then you can see it better. Now a short summary to get good measurement results. Use always the smallest applicable measurement range, because the bigger the numbers in the display, the smaller the error. Twist the wires. Ensure that the experiment is far away from current lines. Think about lamps, extension cables, multiple socket boards, power lines for the lab equipment. Ensure that the experiment is far away from magnetic fields. Think about lab power supply, plug-in power supplies, or power supplies within the lab equipment. And finally, think about the measurement results. Are they practically useful? What you are doing when you measure within an unpowered circuit 21 milliamp and with the powered circuit 50 milliamp. What can you do with this result? That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. Bye bye.